So I want to talk about an introduction to vectors and some information about them. So typically we think about vectors as existing in Rn, where, you know, n is a natural number. So we think of R1, just sort of the trivial case, R2, uh, all the way up to R3. So really, what's interesting is that we like to think about R2 and R3 quite a bit, but we're really interested in these two, but we're also interested in Rn in the general case. So let's first talk about R2. So vectors in R2 are pretty simple. You can think about them as an ordered pair, A, B, and you can think of a line coming out of the origin going up to that point, and it will always make a right triangle. So this vector will have an angle and it will have a distance or a magnitude. So there's a lot of ways to represent this vector. If we say that this thing is equal to v1, one way is to say, as I have there, is that it's the point AB. Another way is that v1 equals, a1 equals ai plus bj. So we put arrows over these because they're the unit vectors in the x and y direction respectively. And really the way that this notation holds true is the fact that the way that vector addition works. So really in terms of my notation, I like this one because it's a little bit more powerful and generalized. The issue with this notation is that the highest degree vector that you can write with this notation is a vector that lives in R3. So you can think of just the vector v2 equals ai plus bj plus ck. So this is the most general form of the vector for, a subset of this when c is 0 is where we are right now, R2. But in R3, things are a bit different. So I think lastly I'll just talk about is that this I and j, they're unit vectors. So I and j they have magnitude 1 and they're in their respective directions. We like to call them basis elements, so that's sort of another name for them. And this is j. So when you multiply each unit vector by a scalar and add them together, because they're in the direction they are, and they're also it really has to do with the fact that they're linearly independent. But with this form, you can basically write any vector in R2. But in R3, we have to make a three-dimensional plot. So we can say that this is the positive z direction, let's say, and this is x and y. So in the x direction, we have a unit vector, which is the I guy. And then we have one in the y direction, which is the j unit vector. And then we have the last one, which is the k unit vector in the z direction. So I really sort of in this video want to talk about different notational techniques. So another way that these are represented is E1, E2, and E3. They're basically known as the the basis set. I mean, we'll talk about that later in linear algebra, but they're basically a set of linearly independent vectors. We can think about them as 1, 0, 0. Don't worry about this now. I'll talk about later. 0, 1, 0, and 0, 0, 1. What's interesting is that I can take some linear combination of E1, E2, and E3 and scale them, and then I can write any vector. If I say this is V1, then basically this is basically the full set. This vector set is not only linearly independent, but it also spans R3. So any vector in this space can be written as a linear combination of these basis elements E1, E2, E3. And it's the same way with these guys here, but you just use E1. Hold on. Right, E1 plus E2, and you scale them by A and B, sort of the same way we have them here. And if that's equal to V1, so obviously E1 equals 1, 0, and E2 equals 0, 1. So this is just stuff to think about in the future. And that's sort of why I like writing them in this form, this AB, because you can obviously see if I have that V1 equals A times 1, 0 plus B times 0, 1. Well, what do I get there? I get AB, which is my arbitrary point in my space. So that's just notation for right now. But really, what's more interesting and more powerful is we want to talk about a more general notation, because this IJK guy is good for R2 and R3. But in more general, let's talk about, if I have Vn. So, well, how about I just say phi? Let's introduce Greek notation, huh? So if I say phi equals, we'll say x1, x2, x3, where x1, x2, x3 exists in the real numbers. Well, this is going to be some vector in R3, right? And if I did like sort of another one, let's say I call another vector phi prime, and that would be equal to, let's say, y1, y2, then we know that this vector would exist in R2. But let's talk about more general vectors. Let's choose gamma. So we have gamma equals x1, x2, all the way up to xn. So it's arbitrarily long. So here, if we say n equals 3, well, then we say that gamma exists in R3. If n equals 7, then gamma exists in R7. So now we have a notation that we can represent arbitrary size vectors and think about how they work. In the general case of n, then gamma exists in R to the n. So with this notation, viewing a vector as sort of a point in space, from the fact that if we have, with the general case, if we have gamma equals AB, well, that's just some point AB in R2. So with this is sort of how really this notation here is how we think about things, because if I prove things for Rn, let's say, then I know that if it's true for Rn, and this is how we do it in math, if we say something about Rn, the general case, then it would be true for R47, R20, R3, and R2. So really, when we talk about things in Rn, we've generalized it to Rn, but it will work in things that we really care about because, right, as human beings, we exist in the three-dimensional world, and we care about the two-dimensional world as well. So this is just sort of the general outline of vectors in terms of notation. So probably in the next video, I'll talk about matrix multiplication. Well, probably I'll talk about dot products and cross products. So I will catch you guys.